Okay, so today we're going to talk about communication and dominant matrix. And with that, they are actually binary matrix, or a type of binary matrix. So what a binary matrix is that it only has ones and zeros. So you can see here in the first couple of examples, we have binary matrices. They've only got ones and zeros. And so binary, they're used in computer programming where you often see only ones and zeros. But in particular, we're going to look at a couple of types of binary matrix. So that's where they have ones and zeros. And the first one we're going to look at is permutation matrices. So they are a type of binary matrix, except that they are square. So we'll have the same number of rows and columns. So if we thought about it, an identity matrix is also a binary matrix because it has ones and zeros, because the ones are on the leading diagonal there. So we can see down there. So with the permutation, what we use them to rearrange other matrices. So if we have a look at this example, we've got the matrix X, which is represented with 3 rows and 1 column, and we have TAR in it. And then we have this permutation matrix, which is a 3 by 3. Now we're going to use this permutation matrix to change the order of the X1. Now if we look at it, we have to pre-multiply, meaning P needs to go at the front, because for this to be defined, we have 3 by 3 and 3 by 1. And if you have a look when we do this, so you would do run and dive if you were timesing. So you go run and dive. And you can see 0 times T is 0 and 0 times A is 0 plus 1 times A. So you, plus 1 times R. So you can see that the R appears in the answer. So then if you were looking at the next one, so if you did run and dive, the zero gets times with the T, so that'd be 0. 1 gets times with the A, so the A ends up present there. Okay, and then if you did the last row, you if you did this row with that column, so the T gets times with 1 plus 0 plus 0, so T ends up present. So you can see that you've rearranged the X matrix to right. Now if you square the permutation matrix, so see here's P and we've squared it, so we've raised it to the power of T there, it will rearrange the letters again, and when we did it squared it, we ended up back at the start with ATR. So and if you'll have a look, they're just noting here, P squared is an identity matrix because we see ones down the leading diagonal. Okay. We're going to have a look at an example, but there's not much room, so I've put it on the next page. So if we look at this example matrix, they've got a permutation matrix in front of another one, which is got letters in it, so it's leap. So if we were checking that this is defined, we've got a 5 by 5 and a 5 by 1. Okay, so we can see, so if you went to enter this into your calculator, it could take quite a long time, which is maybe not what we want to be doing in an exam. So it's easier just to work it out quickly in your head. So if you think, when we multiply, we go run and dive. So you can see that the 1 is going to affect the 4th letter down. So 1, 2, 3, 4. So we're going to see a P come up first. So these two here have a P come up first. So then if I went on to do the next one, so run and dive, we can see that the 1 is on the 3rd letter. So 1, 2, so A will come up. So we see A. And so therefore we can pick that this is the answer. Okay, now we're going to move on to communication matrix, and they are a type of binary matrix as well, and where 1 indicates that something or someone can communicate with another person directly in one step. So that's called one-step communication, and that's the first one. So often we use C as our letter for indicating a communication. So if we're going to set up a matrix, and they will be, a communication matrix will be a square matrix, and we're going to have X, Y, and Z, and then we'll have X, Y, and Z. So if we look at these people, so this is someone from this to that person. Okay, so if you think about it, we'll put a 0. Now, you're not going to communicate with yourself, so we'll put a 0. If we look at our diagram over here, we can see that X can communicate with Y. So we will put a 1 in our communication matrix. Now, X can't directly talk to Z, so we put a 0. If we look at Y, Y can directly talk to X, won't talk to themselves, and can also talk to Z. And if we look at Z, Z cannot talk to X, but can talk to Y and won't talk to themselves. So this matrix C demonstrates a one-step communication matrix. Okay, so we often talk about also two-step communication matrices, and we can actually get two-step communications by squaring the first communication matrix. So if we square it, so essentially that means communication times, or C times Z, yeah? So if we do that, and you can do it on your calculator if you like, we will see this following matrix occur. So we see 1, 0, 1, 0, 2, 0, 1, 0, 1. Okay, so just to explain this, if you look at, you can see that you can use two steps, you can get back to X from X. So what I mean, so here, if we're talking about this thing here, for two steps, if I went, I could go from here and then go back there, and there's one way I can use two steps to get back to X. Now, if you look here in the two-step communication matrix, it says we have two options of using two steps to get from Y back to Y. So we can have a look. So we could go, this would be one option where we went to X and then back to Y, or we could have gone the other option where we went to Z and then back to Y. So that's why we've got two. There's two options for two-step communication. Okay, so just to demonstrate another value, so if I said here between Z and X, there is one two-step option. So if you look to get to Z from X, so yeah, if you look, we could go only from Y to X, and there's that one option of two steps. Okay, so when you have C2, this indicates all the two-step communication options, and when you just have the first one, that just the C up here, that just shows you the one step. So once again, you can find this using your calculator by squaring the first communication. So using calc, just square your C matrix. All right. So this page is just summarizing it up. So analyzing communication matrices, the number of two-step links in a communication system can be identified by squaring the communication matrix. So we saw that, we got the communication, and we squared it. Now, when they ask you for the total number of one and two step communication matrices, what you need to do is just add them. So if we're looking at our example before, our above example on the page before, we can find that total amount of 1 and 2 steps just by adding these two matrices together. So we'd add the C and the C squared because that's our 1 step and our 2 steps. So if we wrote those matrices out, remember when we add matrices we just add the like elements. So that's C, and I'm writing out C squared here. So there was my 2 options we talked about. Okay, so when we do that, we add all the like elements. I get 1, 1, 1, 1, 2, 1, and 1, 1, 1. So if you think about it, this was X, this is Y, and Z. If they were asking you, you know, who has the most total of 1 and 2 steps, well, X has 3, Y has 4, and Z has 3. Okay, here we're going to do another example. Now you have in your notes the first communication matrix C written up for this one, but it's actually incorrect. So we're going to fix it up. You can change the numbers in your page. So we'll set up the first, this is C1 or the first communication matrix. Now they're going to be square, and you have Eva, Wong, Yummy, and Kim, I think it is, and then I'll do across the top as well. Okay, so if you have a look, let's have a look. So a 1 is given if they can directly talk to that person. So these people could all speak different languages, but Wong could speak all of them. So if we look at who can just directly talk to each other. So if we look at Eva, she won't talk to herself. She can talk to Wong, so I'll put a 1, and she can't talk to Yuri directly or to Kim directly, so we'll put a 0 there like that. I think in your page it said they haven't written that right. So if we look at Wong, Wong can talk to Eva, not going to talk to themselves, but Wong can talk to everyone because she speaks all the languages. If you look at Yuri, she cannot, or Yummy, sorry, they can't speak to Eva, but can speak to Wong, won't speak to herself, and can speak to Kim. And then the last one, obviously, can't Kimmy can only directly speak to Wong, and 0, 0. So this is the 1-step communication. This is matrix. Whatever. Okay. So if we want to get how many, the 2 steps, so if we wanted to know how many options are there for me, say, to get Eva, a message to Kimmy from Eva, that would be 2 steps because she's got to go to Wong and then go to, that will then go to Kimmy. So I can get that 2 step by squaring it, and they've done that down here. So C squared, so this down here, so this is actually the communication squared equals this, and this, so this represents the 2-step communication. So there. Okay, so what we also notice is that obviously here in the first communication matrix, we see zeros down the diagonal, and that's a redundance. So a communication link is said to be redundant if the sender and the receiver are the same person. So when you end up at the same spot, you're not going to deliver a message to yourself. So they're called redundant, and you see a 0. So all of the non-zero elements in a leading diagonal of a communication matrix or its power represent a redundant link. So really, we could say down here, those are redundant as well, because we're talking about getting a message and sending it off, and then it just comes back to me, the same person, so they're redundant. So you might not, when they ask, you know, they might say how many redundant 2-step communications, you would just add up all of these and things. So just to know that they're not really relevant, and you might get certain questions. We'll see later on. Okay, so another example here. So if we look here, we can see there's, 4 talkers or whatever. How many of the two-step communication links shown in matrix C2 are redundant? So, there you go. So we had to find out redundant. So the redundant, is down here on that leading diagonal. So if I was doing this example, I'd go 1 plus 2 plus 2 plus 1 equals 6. So there are 6 redundant two-step links. So if you had to find 3-step links, you would just do the communication to the power of 3. If you had to find 4-step, so ever. But however, unless the communication network is really large, it's just a lot of them, the multi-step links will be all redundant because it's just going back to the cells, so we won't really need them. In your exams, mainly everyone's concentrating on 1 and 2-step communications. So that leads us into, here's another example. So we've got these trouts in breeding ponds P, Q and R, and they're connected by pipes shown. So in terms of, we could set up the first communication matrix. So with the trouts, so might go P, Q, R, X and V. So we could set that up and we've got P, Q, R, X and V. So which are we looking at? The trouts that what pond they can directly go to breed in one step. So P, we'll see, can't go to P can go to Q, they can go to R, but they can't in one step go to X or V. For Q, it can go to P, won't go to itself. It can go to, it can't go to R, it can go to X, and it can go to V. So R can go to P, R cannot go to Q, won't go to itself, can go to X, cannot go to V. X can't go to P, can go to Q, can go to R, and can go to V, won't go to itself. Oh, wait a minute, sorry. Won't go to itself, will go to V. So I picked that up, that mistake, because I should have zeros on my leading diagonal. So V to P, 0, V to Q, 1, V to R, 0, V to X, 1, and V to V, 0. So that's your first communication. So when would they ask us, in terms of the breeding pond, what does the sum of the elements in row 3 and row 3 and the sum of these elements represent, they called this, in the original example, they called this matrix W. So that's what they're referring to, sorry. So they're asking you, what does the sum of those represent? Well, it's the sum, if you add them up, so R equals 2, it represents that the trouts in pond R have 2 one-step options to breed in another pond, and another pond, and if you have a look, they are P and X. Okay, so the number 2, the sum of it represents how many ponds they can breed in. When matrix is squared, they meant down here in part B, when they said when matrix W has been squared. So if we do that, in row 2, column 3R, what does this tell us? So it tells us how many 2-step options. So you could get the W squared by squaring this matrix up here. I'll just leave it for today, sorry. You can check with me on Monday or whatever. Okay, this leads us into dominance. Dominance matrices are the same, very similar to communication matrices in the fact that they are binary, so there's only ones and zeros, and then also they are square. But it's often, we'll often use it for tournaments, or they talk about sporting competitions and things. So if we have a look at here, at the example there, so we've got four teams or 4 players, and they're all playing each other in a tennis competition. So obviously there's no time for everyone to play everyone, so we're going to look at what's happened with whoever played and work out dominance. So if you look at A, I'm just going to show A beat C and they also beat D. So along here in this first matrix here, we see a 1 on C and D. Okay, if you look at say B beat E, they beat C, and they beat A, so we'll see a 1 on A, C, and E. All right, so that's setting up very similar to communication, but it's only going one way. There's direction because someone beats someone. Okay, so if you look at that, this first matrix when you set up D is the one-step dominance. So we call it one-step dominance. And if you look here, if we look along here, these would be obviously A, B, C, D, E. We have two, if we look at we have 2 winners if we only look at one step, and that would be B and E. So we might want to take into 2-step dominance into account to see who. So when we do 2-step, because A might have beaten C, but because C beat D, that makes A more dominant and things like that. So we get the 2-step dominance, just like communication. We square the D, and we get it. And then what we do is we add the D and the D squared, so 1-step dominance and 2-step dominance, and we end up with this answer here. And then when we see that, we can see we get a clear winner there. So B ended up being the winner when we add those two. So they're the difference. That's the difference. So the main difference between dominance and communication is there's direction on these, meaning that someone beats someone. It doesn't go both ways. Okay, so here's another example, and I'll set up the dominance with you. So if I was setting up the first dominance matrix, so because I have A, B, C, D, I would set up a square matrix like this, and we generally say this person wins, that person is the loser. Okay, so if you look, A doesn't play themselves, but beat B, didn't beat C, but beat D. B didn't win, doesn't play himself. C did beat B, and so on. And so here, and we're setting up, C didn't beat anyone, and D beat just C and B. Okay, so there we go. So here is actually the dominance matrix. So this is 1-step dominance. To get, if I do D squared, that gives me 2-step dominance. Okay, so if I go, so I've constructed a dominance matrix and takes that, or let's say use a graph to construct a dominance that takes into account both 1 and 2 steps. So that means I've got to add them in. Because they just want one matrix, so I will add these two together. So you add the corresponding elements. So we've got 0, 0, 2, 0. So I'm just 0, 0, 0, 0, and then, oh, sorry. Okay, sorry. So when you add this is D and D squared together, you get this one here. And then I can add it up. This shows me both 1 and 2 step dominance. So if I look at this one tallies up to 5. This one tallies up to 1, 0, and 3. So I could rank the players. So A came first, and then D was second, then B was third, and C fourth, and so on.